Good morning and welcome to PID Control Theory Lecture 6A, where today we'll be looking at a Python simulation of a PID controller. So split this lecture into three parts, Lecture 6A, 6B and 6C, and in 6A we're going to be looking at making a PID controller class, and in the other two lectures, our next two lectures, we'll be using our PID controller class for a heater model and a motor model. So let's get on with this. So we're going to make a class PID controller. And the reason we're using a class is because we can save values like kp, ki, kd, our variables to this class and our class object, and then we can use the PID controller object for whatever model or simulation we like. So many advantages to using a class. So the first main function you would have, or the main member of the class PID controller, is def init. Well, that's the constructor of our class. So in def init, we are basically initializing variables. So when we call this class and we build our object, our first PID controller object, we're going to have to give it some variables. So Python always requires you to use self, and then we're going to give it kp, ki, and then kd. So when you call this object and make a new class PID controller, you'll have to give it kp, ki, and kd, our proportional, integral, and differential parameters. And so that's how our controller now knows what to calculate when it has to make calculations. And another one we're going to give, of course, is the set point. Now, optionally, you can actually put an output limit. So in PID control in the real world, sometimes you put an output limit, so you'd not allow the input power to the process to be above 2000 watt. Now, for now, we're going to just leave it as it is, as kp, proportional variable, integral variable, differential, and the set point. And so that's it. Okay, next we have to initialize our variables. So self.kp will equal simply kp. Self.ki will equal ki. Self.kd equals kd. And so what we're doing here is self.kp is actually a member variable of this class, and we're just going to make it equal to whatever we input kp, ki, and kd to be. And then we do the same for the set point. Self dot set point equals our set point. And again, if you want to use an output limit, feel free to use the output limit. However, I won't be using an output limit here to keep it basic. Now, another important thing you need to have in this class is actually you need to be keeping count of the area of the graph over time. This allows us to use our integral action. So we're going to make this variable called self.integral, and our integral is just, for now we're going to say it's a 0. When we call this class, obviously there is no integration error, so we're just going to make self.integral equals 0. And another one we need to keep track of is self.previous error, and that allows us to use differential control, for example, and our integral. And so that's our constructor def init complete. That's all we need to do. We need to initialize our variables kp, ki, and kd, our set point, and then we make two new variables, the integral and the previous error. And that's all you need to do. Okay, the next thing we need is the compute function, or a calculation function. And that basically calculates, when we call this function, it calculates the PID error and the control signals based on the current value, current output value. So for example, if you have current value, if you have a heater, the current value would be the output temperature, anything of the output that you're trying to measure. And for a motor, it could be the speed. Okay, next we have this dt, and dt is a time step. Now, I won't explain too much about time steps now, but I will in later lectures. But just know that time step is important because computers are actually discrete time systems. They don't work on continuous time. They work through a time step, which is small intervals in time. So what's inside this compute function? Well, first we need to calculate the error, because PID is about error. So error equals to self.setPoint minus the current value. And remember, PID all calculations in PID are rely on the error. So that's one of the most important things. The first thing we calculate is the error, which is equal to set point minus the current value. Okay, the next thing we're going to do is accumulate the error over time, and that's allowing us to do integral, our integral action. So self.integral, which remember we initialized to 0, but now we're going to accumulate our integral, and that plus equal, so we're accumulating the error multiplied by the time step. And so over time, as the time step increases, you'll keep accumulating that integral value, and that allows us to, well, do integral control. Okay, the next thing we need is the derivative. We need to calculate our derivative. And what is derivative? Well, derivative is basically taking the rate of change of the error. So derivative equals error that we just calculated minus this previous error divided by the time step. Now, divide, that is supposed to be. So derivative is not, well, we're not using self.derivative, we're just using derivative because we simply take the error, the current error, and the previous error. So that doesn't need to be a part of the class. That's just derivative, a simple calculation. However, with integral, we're accumulating over time. So this class object needs to keep storing the value of the accumulated error. But derivative just takes the previous error and the current error and then makes a calculation. Okay, now it's important to understand that if dt equals 0, for whatever reason dt equals 0, this entire term here will be whatever the errors is divided by 0. So divided by 0 is, well, it doesn't exist. So we say this: if dt is greater than 0, else derivative equals 0. This avoids us having the divided by 0 error that Python can give you in the case that dt is 0. So do add this part here for safety. Okay, the next thing we need to do is just make self.previous error equals the error. So that's gonna, as you keep using this function, the previous error is changing. That's what we want. Okay, that's all the calculations you really need to do. Okay, next, we've done with our calculations, our individual calculations, and now we're gonna output the full control signal. And so that is output equals this big calculation here. So self.kp multiplied by the error. So that's our proportional calculation, that is kp multiplied by the current error, the plus self.ki, our integral component, multiplied by self.integral, which is our accumulation of errors, plus self.kd, our derivative, multiplied by the derivative. And remember, in our previous lecture, we looked at how we combine all three kp, ki, and kd parameters to make the control signal. And so now output here is, well, that's the control value. And so that's going to be the input to the process, so the input to the heater or the input to the motor. And so, well, what we do here is we simply return the output. Now, if you were to make output limits, for example, so you were to restrict the output power to exceed a certain value, you would return output or the value or the maximum value. So for example, if the output was above the maximum value, well, you'll just clip it at the maximum value. So for now, if we keep it simple, return output, and if you have a limit, return the limit if the output is above the limit. So that's simply it. That's our PID controller class, and in the next two lectures we'll be using this PID controller class into our two different models. Thank you for watching. Hope to see you next time. Thank you.